Protection against overcurrent. Chapter 43 concerns itself with protection against overcurrent, emphasizing the need to protect electrical installations from excessive currents that can cause overheating and damage. 4.3.1 explain the types of overcurrents, including overload and fault currents. An overcurrent is any current exceeding the rated value of a conductor, cable, accessory, or protective device. Chapter 43 focuses on the two main types of overcurrents. Overload currents. An overload current is an overcurrent within an electrically sound circuit, meaning there is no fault present. It occurs when the normal power demand exceeds the circuit's rated capacity. Examples include motors doing too much work or too many appliances plugged into a socket outlet circuit. Overload currents are not substantially larger than the circuit's rated current and can persist for extended periods. Overcurrent protection aims to avoid overload currents of long duration. Fault currents. A fault current is a current resulting from a fault condition, such as a short circuit. Faults include line-to-neutral or line-to-line shorts in three-phase systems, or any line conductor shorting to earth. Fault currents are typically much higher than overload currents due to the low impedance of the fault path. Circuits are deliberately designed with low impedance to induce high fault currents, ensuring rapid disconnection by protective devices. Protective devices must be able to tolerate the prospective fault current at the point of installation. Understanding the distinction between overload and fault currents is crucial for selecting appropriate protective devices and ensuring effective overcurrent protection. 4.3.2 discuss the selection of protective devices and the importance of coordination between devices and conductors. Selection of protective devices. Protective devices like fuses and circuit breakers are essential to interrupt overcurrents and protect the installation. BS88 fuses, BSEN60898, BSEN60947 to 2 circuit breakers, and BSEN61009 RCDs are examples of compliant protective devices. The rated current I_N of the protective device must be less than or equal to the lowest rated conductor's current carrying capacity in the circuit. Coordination between devices and conductors. Coordination ensures that protective devices operate in a manner that protects both conductors and equipment. The rated current or setting of the protective device, I_N, must not be less than the design current, I_B. Overload protection should only occur on socket outlet circuits or motor circuits. The devices work with a speed and accuracy that, if coordination is achieved, can prevent issues related to excessive current. Device characteristics. When selecting a protective device, it's important to consider how the protective devices behave and the impact that their behavior can have on selected cables. Factors in temperature. You may need to apply a factor to bring the temperature range down to a value, given in Appendix 4. Ambient temperature can affect the ability of the cable to dissipate heat. Selectivity. Discrimination, now called selectivity, ensures that the protective device closest to the fault operates first, limiting the extent of the outage. Protective devices should be selected and erected, such as to limit the risk of unwanted tripping. In a coordinated system, the downstream protective device should disconnect the fault before the upstream device operates. 4.3.3 cover considerations for ring final circuits and the calculation of disconnection times. Ring final circuits. BS1363 socket outlets may be supplied through ring final circuits. Ring final circuits were introduced for a reason but are a potential risk. Diversity shouldn't be factored into electric vehicle charging systems due to the demand. Calculation of disconnection times. Disconnection time refers to the time taken by a protective device to interrupt a fault current. The maximum disconnection times are specified in Table 41.1 of BS7671. These times vary depending on the type of circuit, final or distribution, and the earthing system, TN or TT. For TN systems, the disconnection times are 0.4 seconds for final circuits, up to 32A for socket outlets and 63A for fixed equipment, and 5 seconds for distribution circuits. For TT systems, the disconnection time is 1 second for distribution circuits. To verify disconnection times, the earth fault loop impedance, Z_S, must be low enough to ensure sufficient fault current for the protective device to operate within the required time. The formula for verifying earth fault loop impedance is provided in Appendix 3, Z_S less than or equal to U_O/I_A, where Z_S is the earth fault loop impedance, U_O is the nominal voltage, I_A is the current causing automatic operation of the disconnecting device. By carefully selecting protective devices, ensuring coordination, and verifying disconnection times, electrical installations can be effectively protected against overcurrents, thus reducing the risk of thermal damage and electric shock.